problem, let's see, this is problem 9. You got a pendulum, length 120 centimeters, pulled back 20 centimeters from equilibrium. The weight of the ball is, or the bob is 12 newtons. We're asked how much higher the pendulum is here than at its equilibrium position. And we use the Pythagorean theorem, and we figure that this side is approximately 118 centimeters, 118.3, 118.4 centimeters, which means it's about 2 centimeters. Okay, if the pendulum swings back here, of course, then you have the full length here, the full 120 centimeters from here to here, which means that the vertical displacement is 2 centimeters. Roughly 2 centimeters. Now I'm just going to use the 2 centimeters, but if you want to do an accurate analysis of this, you want to get the next decimal place here. You want to use enough significant figures in your calculations that you get a sufficient number of significant figures in the difference between these two numbers. Okay? Now, you're asked to sketch the vector that represents the displacement from equilibrium position to the pullback position. And that vector, got the wrong color here, that vector would be this. Now, this vector doesn't represent the path from here to here, which is an arc of a circle. The vector's straight vector from this point to this point. We don't have to worry about the path to answer the questions we have in this problem. So here's our displacement vector, so that this vector, if we use I and j coordinates with the horizontal and vertical coordinate system, is going to be, well, approximately 20 centimeters times the I vector plus 2 centimeters times the j vector. Now the I vector is actually going to be, the I component is actually going to be a little bit less than 20 centimeters. It's probably going to be, let's see, this is 1% of this. It's going to make 0.5%, and 0.5% of 20 is 0.1, 19.9. I might have my decimals in the wrong place, but I don't want to take time on the tape to think that through. Anyhow, you can figure that out fairly easily using the Pythagorean theorem, and you'll find that there's not much error in this. We want to find now the work done by gravity, so we want to put the weight vector in here. And that weight vector is going to be a 12 Newton vector. Let's project the weight of the displacement vector onto the weight vector. And here we have our delta y vector. And what is the magnitude of the delta y vector? That's just going to be the j component of this vector. Since the weight is parallel to the x-axis, the delta y vector is going to be the 2 centimeters. And of course the delta y vector, if we want, is 2 centimeters times j. So that the work done by gravity on the pendulum is negative 12 newtons times j plus 2 centimeters times j. And what dotted with the delta y vector. Or we could do the negative 12 newtons times j dotted with this vector. And you should probably do that. You get the same thing. The gravitational vector has 0 I component, so the I component, the product of the I components is going to be 0. And you want to think about those connections with the dot product. in any case, this work is, okay, 2 centimeters is 0.02 meters. 0.02 times 12 is 0.24. So we get 0.24 joules, and it's negative. And you can understand it's negative. Again, the weight and the delta y are in opposite directions. But of course, all that comes right out of writing these vectors with their components and applying what we know about the dot product. Okay, so the other part of this then is that the change in potential energy is the negative of the gravitational work on the system, which is 0.24 joules. Now, I'll first note that a more accurate calculation of the 118 centimeters is going to lead you to closer to 0.20 joules than 0.24 joules. Now, the change in potential energy from here to here is plus 0.24 joules. The change in potential energy going back, if we release from here at rest and come back, is negative 0.24 joules. So for the trip back, I'll kind of circle this and point over here, indicating that we're talking now about the trip back. The work done by non-conservative forces on the system is going to be negative 0.1 joules. That's according to the assumption that we have a 0.1 joule amount of work done on the system as the pendulum swings back. Okay, I'm not going to address the case where there's no friction loss. It's very similar. I'll mention it at the end. In this case, and you should be able to fill in the dots now, the change in kinetic energy is going to equal the negative of the change of potential energy. Change of potential energy swinging back here is negative 0.24 joules. So the negative of the potential energy change is going to be plus 0.24 joules, minus the 0.1 joule, the work, non-conservative work done on the system, the work done by the air resistance. And that's going to leave us a kinetic energy change of 0.14 joules. If we release it from rest, of course, the initial kinetic energy is 0, and it doesn't take much to conclude that 1/2 mvf squared is going to have to then equal the change in kinetic energy. Did I say 1/2 mvf squared? I don't remember if I said the square, but we understand that. And of course, if the air resistance is absent, we don't have the negative 0.1 joules here. We get the whole 0.24 joules back in the form of kinetic energy, and then the 1/2 mvf squared is going to be 0.24 joules. And of course, you know that the mass is going to equal the 12 newtons divided by the 9.8 meter per second squared acceleration of gravity.